Welcome back. Our next topic is complex matrices, and in particular Hermitian matrices. So I'm going to start with a very quick review of complex numbers. So we write a complex number as a plus ib, and the complex conjugate is a minus ib. Z times the complex conjugate z bar, which is a plus ib times a minus ib. If you work that out, you get this, and you get a squared, and then the middle two terms cancel, and I times minus I is plus 1, so you get a squared plus b squared, which notice is a non-negative real number. So we're going to write z with a bar or 2 bars for the absolute value, and that's going to be a squared plus b squared, the square root of a squared plus b squared. So we have this identity that zz bar is absolute value of z squared. Another fact, which is kind of handy, is if you multiply z times z bar over absolute z squared, you get zz bar over zz bar, which is 1. So that tells you how to compute the inverse of a complex number. You divide z by the real number, absolute value of z squared, z bar. So for example, 1 plus I inverse is 1 minus I over 2. And the final thing about basic complex numbers is the polar decomposition. You can write a complex number as r e to the I theta, where r is a non-negative real number and theta is between 0 and 2 pi. And I'll draw a picture to remind you how this goes. If you draw the complex numbers in the x plus iy plane, the point xy, or x plus iy, well, you compute r is the square root of x squared plus y squared, which is to say the absolute value of z, and the tangent of theta is y over x. So theta is tan inverse y over x, but make sure to make it between 0 and 2 pi. All right, so let's go on to discuss complex vector spaces. So Cn, of course, is just the n tuples of complex numbers. We've already used this a bit. And the important thing is what the notion of length of a complex vector is. So let's talk about that for a minute. What is the proper notion of length? Well, remember in Rn, the length of a vector, it's the square root of x1 squared up to xn squared. And notice that the thing on the inside is a non-negative real number, and so it has a unique positive or non-negative square root. If you do the sort of naive thing in Cn and define the length of a vector to be the square root of z1 squared plus zn squared, you immediately run into trouble, because this number z1 squared plus zn squared is complex. And there's no decent, unique way to take a square root of a complex number. That's one problem. Another big problem with this naive definition is the following. Notice that in Rn, a vector is 0 if and only if the length of a vector is 0 if and only if it's the 0 vector. But in C2, for example, you could take the vector 1i, and with this silly definition of length, the length of this vector is 1 squared plus I squared, which is 0. So you'd have a vector of 0 length, and that's definitely bad. So that's obviously not the right thing to do, but it's kind of clear what you should do. We need to somehow get a non-negative real number so we can take its square root. And the natural thing to do, well, let's see, in C1, what did we do? We plotted it like this, and we defined the absolute value of a complex number to be the square root of x squared plus y squared. Well, a vector is, if you take the length of a vector, it's a generalization of this. This is a 1 vector. So to generalize this to an n vector, it's clear what to do. If v is z1 through zn, then the length of v had better be the square root of the absolute value of z1 squared up to ... zn squared. Now that's a decent definition. The thing on the inside is a non-negative real number, and so it has a unique non-negative square root. Yeah. And to be explicit, this thing, it's x1 squared plus y1 squared plus dot 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 up to yn squared. And the square root of that whole thing, if you write each zi as xi plus yi. Okay, now another thing to note is that in Vn, another way to write the length squared is v dot v, or we wrote that as the inner product of v and v. And so let's see how that carries over to Cn. You can't use the same formula because v dot v is z1 squared through zn squared, not absolute value of z1 squared, and so on. So we have to modify this. Okay, so how do we do that? We want to get absolute z1 squared through zn squared. Well, that's z1 bar z1 up to zn bar zn. And so you just write that as z1 bar up to zn bar dot with z1 through zn. So it's just like what we had before, except you have to put the bars on one of the terms. And I'm going to emphasize column matrices here. And so if you use column matrices, we write this as this vertical vector here is v, and then this vector here is transpose bar. So the formula for the length squared is v transpose bar times v. Okay, so that motivates the following definition. If v is a complex vector, define v upper h to be the conjugate transpose. That is to say, z1 through zn upper h is z1 bar through zn bar, written as a row vector. Okay, so with this convention, the length squared is given by vh times v. All right, so now let's talk about matrices. Remember back in Rn, we had the notion of a transpose of a matrix, and it satisfies AV transposes V transpose A transpose. So let's define the conjugate transpose upper H of a matrix like this. It's A bar upper transpose. So the conjugate transpose of A, B, C, D is you take the transpose and the conjugate. And then you have this identity. When you take upper H, you switch the order of the two factors. All right, now going back to Rn again, we say a matrix is symmetric if A transpose is equal to A. And the corresponding thing for Cn is you say a matrix is Hermitian if AH is equal to A. So we have the following analogies. For Rn, we have the transpose and the notion of symmetric. And the corresponding concepts in Cn are the conjugate transpose upper H and the notion of being Hermitian. All right, so here are some Hermitian matrices are quite important, just like symmetric matrices. And so here are some key facts about Hermitian matrices. So the sort of fundamental one is the following interesting identity. If A is Hermitian, then and V upper H A times V is always a real number. For any complex vector V, this thing is a real number. So let's see, let's do a 2x2 example. A 2x2 Hermitian matrix, well, if A is this, the conjugate transpose is this, and those are real, those are equal if, well, you need A is equal to A bar and C is equal to B bar and so on. So you see that A has to have real numbers on the diagonal, so let's call those X and Y, and B bar on the antidiagonal where B is allowed to be complex. So let's check this identity. If you have any complex matrix alpha beta, and you write this down, you get alpha bar beta bar times this matrix times alpha beta, and you write that out, and you get alpha bar x plus beta bar b bar, and so on, and this times alpha beta. And when you multiply these two out, you get absolute value of alpha squared x plus alpha beta bar b bar plus alpha bar b beta plus absolute beta squared y. I'm claiming this is real. Well, the first and last terms are real, and the sum of the two middle terms are real, because the complex conjugate of the first term is the second. So when you add up a number and its conjugate, that becomes real. Okay, so that's a 2x2 example, but why is this true in general? It's kind of a neat proof. So I'm claiming that VHAV is real. Well, let's take its bar. VHAV bar is V bar upper H, A bar, V bar. And this is a scalar. It looks like a matrix, but it's a scalar, of course. And it's a 1x1 complex number, so it's symmetric. Any 1x1 matrix is symmetric. So we can take its transpose, it's equal to itself. When you take the transpose, you get this, and the first guy is VH, and A bar transpose is equal to A by assumption, and the last guy is V. And so there you go. We've computed that the bar of the thing we started with and the thing we started with are equal. Cute, huh? Okay. The next important thing is if you have a Hermitian matrix, all of its eigenvalues are necessarily real. So it's a complex matrix, but its eigenvalues are guaranteed to be real. So let's see. Suppose AV is equal to lambda V. Just multiply this equation on the left by VH. VHAV is equal to lambda VHV. Let's see. VHAV is real by the first part. And notice VHV, of course, is the length of V squared, and that's real. So everything in this equation is real, except for possibly lambda, and that forces lambda to be real. That's a very simple fact once you have number 1. And now there's a final very important thing, which is orthogonality of eigenvectors. So remember, in Rn you say two vectors are orthogonal if V transpose W is equal to 0. And in Cn, the corresponding thing is VHW is equal to 0. And the assertion is that if A is Hermitian and lambda 1 and lambda 2 are eigenvalues, distinct eigenvalues, then the lambda 1 eigenspace and the lambda 2 eigenspace are orthogonal. In other words, if AV is equal to lambda 1V and AW is equal to lambda 2W, then VHW has to be 0. And here's why that's true. Well, let's see. Let's compute VHW. Well, let's multiply it on the left first by lambda 1. Then what do we have? We have lambda 1 V upper H times W, since lambda 1 is real. And lambda 1V is AV upper HW. And that's VHAW by the usual thing. And if you put in your parentheses here, you get VH times lambda 2W. And let's see, you pull the lambda 2 out and you get lambda 2 VHW. So there we go. We have lambda 1 times something is equal to lambda 2 times something. And if lambda 1 is not equal to lambda 2, then the something must be 0. Okay, so an important special case of that, something which we hadn't mentioned before, although we certainly could have, is just apply this to a real matrix. If you have a real symmetric matrix, first of all, the eigenvalues are real, and second of all, the distinct eigenvectors are orthogonal. Or in other words, the eigenspaces with distinct eigenvalues are orthogonal. All right, that's a good place to stop. I will see you in class.